We are living at the edge of a new cosmic dawn. For millennia, we've looked up at the stars and wondered if we are alone, if there's more to the universe than our small, fragile world. But now, for the first time in human history, we're not just asking those questions, we're actively seeking the answers. And some of those answers, when they come, won't just satisfy our curiosity. They will redefine what it means to be human. They will change everything. Think about it. We're living in an age where our technology is expanding faster than our imagination, where discoveries once confined to science fiction are now within our reach. And it's not a question of if one of these discoveries will happen, it's when. When it does, it won't just be a headline, it will be a turning point in the story of our species. That's what we're exploring today, the space events that could fundamentally reshape human civilization. These aren't just scientific milestones, they're moments that could rewrite our politics, our economies, our philosophy, even our understanding of life itself. Imagine contact with an extraterrestrial intelligence, the discovery of habitable worlds, the first permanent human settlement on Mars, the detection of biosignatures on a distant exoplanet. Each of these events carries the potential to alter the course of history in ways we can scarcely predict. They're not just possibilities, they're probabilities waiting on the horizon. And in this video, we're counting down 30 of the most transformative cosmic events that could change human history forever. This journey is about more than just astronomy or physics. It's about us, our dreams, our fears, our boundless curiosity. It's about the shared human drive to explore, to understand, and to push beyond the known. From the depths of our oceans to the farthest reaches of space, we are driven by a need to know what lies beyond. And as we stand on the brink of these discoveries, it's worth asking, what will we become when the universe finally answers back? Strap in, we're about to embark on a countdown that doesn't just explore the future of space, it explores the future of humanity. So let's begin our countdown with the single most anticipated discovery in all of science, the confirmed detection of extraterrestrial life. And we're not talking about little green men arriving in saucers. We're talking about the far more plausible and imminent discovery of microbial life within our own solar system. This isn't a distant fantasy. Right now, as you watch this, robots are on the hunt. NASA's Perseverance rover is meticulously collecting rock samples from an ancient Martian river delta in Jezero crater, a place scientists believe was once a perfect habitat for life. Meanwhile, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, is on its long journey to explore the icy ocean worlds of Ganymede, Callisto, and Europa. These missions represent our best chance in the near future to answer that age-old question, are we alone? The moment we have that first confirmed positive signal, perhaps a complex organic molecule with an unmistakably biological origin, the world will change overnight. Biologically, it would be the greatest revelation since Darwin. A second, independent genesis of life would mean that the recipe for life is not a rare, fluke event unique to Earth, but a common process written into the fundamental chemistry of the universe. We would finally have a second data point, a comparative biology that would allow us to understand which aspects of life are universal and which are mere terrestrial accidents. Does alien life use DNA? Does it have the same amino acids, or did it find a completely different path to complexity? This would open up an entirely new field of science, comparative astrobiology. But the shockwaves would extend far beyond the laboratory. Philosophically, the discovery would force a Copernican revolution of the soul. We have slowly moved from believing Earth was the center of the universe to accepting we orbit an average star in a remote corner of a common galaxy. Finding life next door would complete that journey, humbling us by showing that life itself is not centered here. Our place in the cosmos would be forever diminished in scale, yet simultaneously elevated in connection. We would no longer be a lonely miracle, but part of a vast living cosmos. This new cosmic perspective could unite humanity under a common planetary identity, a shared realization that we are all crew on a single life-bearing spaceship called Earth. And what of religion? For many faiths, the discovery would be embraced as a celebration of a creator's boundless imagination. For others, it might present a profound theological challenge, forcing a re-examination of scriptures and doctrines that seem uniquely Earth-centric. The very definitions of creation, soul, and human exceptionalism would be up for debate. The ensuing dialogue between science and religion would be one of the most fascinating and important in centuries. This single discovery of a tiny microbe on a distant world would do more than just rewrite textbooks. It would rewrite our understanding of reality itself, proving once and for all that the universe is and has always been a living place. But finding microbial life would only be the beginning. The ultimate discovery, the one that has captivated our imagination for generations, would be picking up a signal that is unmistakably the product of a mind not our own. This is the promise of the search for extraterrestrial intelligence, or SETI, a decades-long endeavor to scan the cosmos for a transmission that would change everything. Imagine the scene. In a quiet control room, a computer algorithm flags an anomaly. It's not random cosmic noise, but a structured signal, a sequence of prime numbers or a complex mathematical constant pulsed from a star system dozens of light years away. The verification process is exhaustive, but it holds. We are not listening to a natural phenomenon. We are listening to a message. The immediate impact would be a seismic shift in human consciousness. Every assumption about our singular significance in the cosmos would vanish in an instant. The universe, once a vast and empty stage for our human drama, would suddenly feel crowded, inhabited, and deeply ancient. That signal would have traveled for decades, perhaps centuries, meaning the civilization that sent it is likely far older and more advanced than our own. We would be like an isolated tribe hearing an airplane for the first time, aware that a technology exists so far beyond our understanding it might as well be magic. This realization would be simultaneously terrifying and exhilarating, a profound humbling that could either unite humanity in a shared moment of awe or fracture it into competing ideologies vying to interpret what it means. Beyond philosophy, the practical implications are staggering. Contained within that signal could be a treasure trove of knowledge, a cosmic encyclopedia offering solutions to problems that plague our species. They might have unlocked the secrets of clean, limitless energy, solved the mysteries of gravity for faster-than-light travel, or discovered cures for our most virulent diseases. Access to such technology could launch us into a new golden age, solving resource scarcity and ending energy wars overnight, but it would also present an immense danger. How would our global economy, built on the scarcity of oil and gas, adapt to the sudden arrival of free energy? The very foundations of our power structures could crumble, creating a period of tumultuous and unpredictable change. The message might not even be intended for us. We could be eavesdropping on a galactic communication network, overhearing a conversation between civilizations that renders our own existence trivial. The long-term challenge would be how, or even if, we should reply. The debate would engulf every level of society, from the halls of the United Nations to kitchen tables around the world. Who gets to speak for Earth? What do we say? Do we announce our presence with hopeful optimism, or do we observe in silent caution, heeding the warnings of those who fear that any advanced civilization we encounter might not be benevolent? This single event would force us to grow up as a species, to finally see ourselves not as separate nations, but as a single planet, a collective humanity with a shared future and a common voice. It would be the ultimate test of our maturity, demanding a unity we have never before achieved. Yet the drive to establish a permanent human presence on Mars is about so much more than mere survival. It represents the greatest scientific expedition in human history. A permanently occupied research base would transform our understanding of the red planet. Imagine teams of geologists unconstrained by pre-programmed rover routes, scaling the towering slopes of Olympus Mons to read the history of the solar system in its rock layers. Astrobiologists could spend years directly investigating the subsurface aquifers, searching not just for fossilized evidence of past life, but for extant, deep-dwelling organisms in a potential second biosphere. The sheer volume and quality of data returned by human intuition, curiosity, and dexterity would dwarf centuries of robotic exploration, unlocking secrets about planetary formation, climate change, and the potential for life that we can scarcely imagine. Beyond the science, the social and psychological dimensions of this endeavor are profound. The first Martian colonists will form the most isolated community in human history, a tiny outpost separated from Earth by months of travel time and a communication delay that makes real-time conversation impossible. They will have to develop entirely new forms of governance, economics, and social structures to survive. Will they use a resource-based economy? How will they handle conflict resolution or medical emergencies with no possibility of evacuation? Their successes and failures will provide a live blueprint for how humanity might organize itself in a future where we live among the stars, offering invaluable lessons that we can apply to solving problems here on Earth. Perhaps the most powerful impact, however, will be on the human spirit itself. Watching a sustainable community grow on another world would be the ultimate symbol of hope and resilience. It would prove that our future is not confined to a single planet, that our species possesses the ingenuity and the courage to ensure its long-term survival against existential threats. This achievement could serve as a powerful unifying force for all of humanity. Just as the Apollo moon landings briefly made us see past our terrestrial conflicts to marvel at what we could accomplish together, a thriving Mars colony would present a common, aspirational goal that transcends national borders. We would no longer be citizens of individual nations looking up at the same sky, but a multi-planetary species with a shared destiny written in the stars. Right now, the stars are effectively unreachable, their distances measured in the lifetimes it would take to reach them with our current technology. But what if the universe provided a shortcut? The fourth event on our countdown is the discovery of a stable, traversable wormhole, a cosmic tunnel connecting two distant points in space-time, or the revolutionary development of a practical faster-than-light travel technology like a theoretical warp drive. This wouldn't just be an upgrade to our rockets, it would be a fundamental rewrite of the rules of exploration, turning the entire galaxy into our backyard. Imagine a natural phenomenon, perhaps a faint gravitational anomaly detected at the edge of our solar system, that upon closer investigation reveals itself to be a stable gateway. This wouldn't be science fiction's swirling vortex of light, but something far stranger, a region of space where the normal rules of geometry break down, a shortcut through the folded fabric of the cosmos. Alternatively, picture a laboratory breakthrough where physicists finally crack the code of metric engineering, learning how to contract space-time in front of a ship and expand it behind, effectively placing the vessel in a bubble of flat space that can ride a wave at velocities exceeding the speed of light without violating relativity. Either scenario would shatter the tyranny of distance that has confined humanity to our solar system for our entire history. The immediate transformation would be to the very concept of exploration. No longer would missions to other stars be one-way generational voyages or lonely trips for uploaded consciousnesses in frozen ships. They could become journeys of discovery and return. A crew could pass through a wormhole near Pluto and emerge minutes later in the Alpha Centauri system, 4.37 light-years away, able to send back real-time data and perhaps even return home for debriefing. This changes everything from the psychology of the astronauts, who would no longer be permanent exiles, to the economics of the mission, which could be funded by the promise of returned resources and knowledge. The galaxy would suddenly become a place of pathways and destinations, a navigable ocean instead of an insurmountable void. This newfound accessibility would ignite a new age of expansion, a second great diaspora for humanity. The first target would be habitable exoplanets, worlds we've only been able to study as faint specks of light. Instead of inferring the possibility of oceans and atmospheres from telescopic data, we could send probes and then people through these gateways to walk on those alien shores. We could establish outposts not just based on proximity, but on true suitability for life, choosing from a catalogue of Earth-like worlds scattered across the spiral arms. The potential for scientific discovery is almost incomprehensible. Field geologists could study the cliffs of a moon orbiting a gas giant in another system, while xenobiologists could directly observe ecosystems that evolved under entirely different suns. Our understanding of physics, biology, and planetary science would accelerate at a rate unimaginable today. Yet, with this incredible power comes profound responsibility and risk. The discovery of a wormhole network would imply we are not its creators but its users. Who or what might have built it? Are we stepping into a crowded galactic subway system? And if so, what are the rules of the road? The potential for conflict over control of these portals would be immense. Would they be managed by a single global government for the benefit of all humankind? Or would they become the ultimate strategic choke points, fought over by rival nations or corporations seeking to monopolize access to the riches of other star systems? The very structure of human society would be tested as we grapple with how to govern something that fundamentally alters our place in the universe. Opening a door to the stars is exhilarating, but we must be prepared for what or who we might find on the other side. For our entire history, humanity has lived with an unspoken vulnerability, a silent acknowledgement that our existence could be violently reset by forces entirely beyond our control. We've found the craters, we've pieced together the history. The cataclysm that ended the reign of the dinosaurs serves as a permanent reminder that Earth exists in a cosmic shooting gallery. But what if we could finally take aim? The fifth world-changing event is the full-scale deployment of a reliable planetary defense system, a global shield that would mark the first time in 4 billion years of life on Earth that a resident species could look an extinction-level threat in the eye and deflect it. This isn't about building a bigger bunker, it's about growing up as a civilization and taking active responsibility for our collective future. The foundation for this incredible capability is being laid right now. NASA's Double Asteroid Redirection Test, or DART mission, was the first critical proof of concept. In 2022, a spacecraft no larger than a vending machine was deliberately crashed into a small moonlet called Dimorphos, which orbits a larger asteroid named Didymos. The goal wasn't destruction, but a subtle nudge, a test to see if we could slightly alter an object's trajectory through sheer kinetic impact. The result was a spectacular success, far exceeding expectations. The impact shortened Dimorphos's orbit by a significant margin, proving that we possess the navigational precision and the basic physics to change the course of a celestial body. This single mission transformed planetary defense from a theoretical discussion into a demonstrable engineering reality. Building on this success, the next steps are already in motion. The European Space Agency's Hera mission is scheduled to rendezvous with the Didymos system to perform a detailed post-impact assessment, giving us crucial data on the asteroid's composition, mass, and the crater left by DART. This information is vital because not all asteroids are created equal. Some are solid chunks of iron and rock, while others are mere rubble piles, loose collections of debris held together by Chinese letter gravity. The strategy needed to deflect one type could be completely ineffective against another. The future of planetary defense will likely involve a whole toolkit of techniques. For a long warning time scenario, we might use a gravity tractor, a spacecraft that flies alongside an asteroid for years, using its own minuscule gravitational pull to gently tug the object onto a safer path. For a more imminent threat, we might need to deploy a series of focused nuclear explosions near the surface to vaporize material and create a thrust-producing jet, or even use powerful ion beams to erode the surface and generate push. The successful activation of a global defense network would represent a psychological watershed for our species. It would fundamentally change our relationship with the universe from one of passive vulnerability to one of active stewardship. The existential dread of a random impact, a fear that has haunted our subconscious since we first understood the craters on the moon, would begin to lift. We would no longer be just tenants on this planet. We would become its guardians, actively maintaining a safe environment for all life. This collective accomplishment could serve as a powerful blueprint for international cooperation, requiring the shared resources, expertise, and trust of every spacefaring nation on Earth. The same global coordination needed to track threats, launch missions, and execute a deflection could pave the way for tackling other existential challenges, from climate change to pandemic preparedness, proving that when faced with a common enemy, humanity can unite and overcome. Ultimately, securing our planet from asteroid impacts is about more than just survival. It's about securing our potential. It ensures that the long, improbable story of life on Earth, from the first single-celled organism to the civilization that can now look out and defend itself, is granted a future. It protects the billions of years of evolution and millennia of cultural development that have led to this moment, guaranteeing that our journey does not end prematurely with a random blow from the cosmos. By mastering this technology, we aren't just saving ourselves, we are preserving the only known cradle of life and consciousness in the universe, granting it the safety and the time needed to eventually grow beyond its cradle and reach for the stars. For centuries, human civilization and all its conflicts have been fundamentally shaped by a simple, brutal reality: the scarcity of resources. Our wars have been fought over land, over oil, over diamonds and minerals. Our economies are built on the precarious foundation of finite reserves buried in the crust of a single planet. But what if we could break free from that limitation entirely? The sixth event on our countdown promises to do just that by turning our gaze to the riches floating just beyond our atmosphere. We're talking about the dawn of asteroid mining, an endeavor that would not just create new wealth, but could fundamentally abolish the very concept of resource scarcity that has defined human history. The scale of this potential is almost incomprehensible. Consider a single metallic asteroid like the famed 16 Psyche. Observations suggest it is not a rock, but a massive, exposed planetary core composed primarily of iron, nickel, and staggering quantities of precious metals. Scientists estimate it could contain enough gold and platinum group metals to be worth quintillions of dollars at today's market values. To be clear, that's a number with 18 zeros. If such a quantity were suddenly introduced to Earth's markets, it would cause economic chaos, completely collapsing the value of these metals. But that's precisely the point. The goal isn't to bring it all back at once and crash our systems. The true revolution lies in using these resources in space to build a new economy entirely off-world. The immediate and most profound impact would be the death of scarcity for certain critical materials. Platinum group metals are not just for jewelry. They are vital components in everything from catalytic converters that clean our air to medical devices, electronics, and the fuel cells of a green energy future. Their rarity and concentration in only a few politically unstable regions on Earth make them expensive and a source of conflict. Accessing a near-infinite supply from asteroids would decouple human progress from terrestrial mining, making these advanced technologies cheaper and more accessible to everyone on the planet. We could finally transition to a truly post-scarcity society for key commodities, removing a major driver of geopolitical tension and inequality. This would ignite the first true space-based economy. Instead of agonizing over the tremendous cost of launching every kilogram of material from Earth's deep gravity well, we could manufacture everything in space using resources harvested in zero-G. Imagine massive, automated refineries parked in stable orbits, processing asteroid ore into pure metal ingots. These would feed orbital factories that 3D print gigantic satellite components, solar power stations, and even the hulls of interstellar generation ships. The construction of a permanent moon base or a Mars colony would become exponentially cheaper and faster if we could source the metals and water for radiation shielding, fuel, and life support from nearby asteroids instead of hauling it all up from Earth at a cost of thousands of dollars per pound. This new economic sphere would create entirely new professions and industries: asteroid prospectors, orbital refinery operators, zero-G construction crews, and space-based logistics coordinators. It would be a modern-day gold rush, but one where the stakes are not just wealth, but the very infrastructure of our future in space. Corporations and nations would compete not for patches of land, but for favorable orbits and the mineral rights to specific near-Earth objects. This could foster unprecedented international cooperation in regulating this new frontier, or it could spark a new era of corporate and national rivalries played out in the high frontier, a sobering possibility that would require careful foresight and governance. Ultimately, mastering asteroid mining is about more than wealth, it's about maturity. It represents a species learning to live off the land in the solar system, to use the resources readily available in its cosmic neighborhood instead of stripping bare its home planet. It's the practical, economic engine that would fuel every other grand ambition on this list, from planetary defense to interstellar travel. By unlocking the treasure chests of the asteroids, we wouldn't just be making money, we would be buying ourselves a future, funding our own evolution from a single planet species to an interplanetary civilization. Imagine a future where the energy needs of our entire civilization are met not by sprawling fields of solar panels on Earth, but by immense, silent power stations floating in the eternal sunlight of space. This is the promise of space-based solar power, a concept that sounds like pure science fiction but is steadily marching toward reality. The fundamental idea is brilliantly simple. Place gigantic solar arrays in geostationary orbit where they are bathed in intense, uninterrupted sunlight 24 hours a day, unhindered by clouds, night, or atmospheric filtering. These arrays would convert that solar energy into microwaves or lasers, and then beam it wirelessly down to receiving stations on Earth called rectennas, which would convert it back into electricity and feed it directly into the global power grid. This single technological achievement could be the master key that unlocks a future free from energy scarcity. The sheer scale of the benefit is difficult to overstate. Unlike terrestrial renewable sources, a space-based system provides baseload power. It's constant, reliable, and available regardless of the weather or time of day on the ground. A single, large-scale solar power satellite could generate multiple gigawatts of power continuously, enough to electrify a major metropolitan area. A constellation of them could meet the entire planet's energy demands, effectively ending our reliance on fossil fuels. This would not just be an environmental victory, it would be a geopolitical earthquake. Nations that currently wield immense power due to their oil and gas reserves would see their influence dramatically wane. The economic and political leverage held by petrostates would evaporate, potentially stabilizing volatile regions and removing a primary driver of international conflict that has persisted for over a century. Perhaps the most transformative aspect would be its impact on global equity. For developing nations, the infrastructure hurdle for energy access is enormous. Building sprawling power plants and complex grid systems is prohibitively expensive and time-consuming. But with space-based solar power, a country could essentially lease a patch of land for a rectenna, a relatively simple structure, and receive a constant, massive inflow of clean electricity. This would allow nations to leapfrog the entire dirty phase of industrial development, bringing power to remote villages and burgeoning cities alike without ever building a coal plant or a dam. It could eradicate energy poverty almost overnight, creating a more level global playing field and fostering unprecedented economic growth in the world's poorest regions. The path to building this system will itself be a catalyst for progress. Constructing such massive structures spanning kilometers across will require a robust space manufacturing industry, likely one fueled by the very asteroid mining we just discussed. It will drive advances in robotics, in space assembly, and wireless power transmission technology. While the initial investment would be colossal, the long-term payoff is a permanent solution to humanity's largest existential challenge: sustainable energy production. The dawn of space-based solar power wouldn't just change how we flip a light switch. It would rewire the entire foundation of human civilization, fostering a new era of global cooperation, economic fairness, and environmental stewardship, finally granting us the abundance of power needed to secure our future on Earth and beyond. And as we turn our eyes from the resources within our solar system to the world's orbiting distant stars, we arrive at a discovery that would capture the heart of every human on the planet: the confirmation of Earth 2.0. This isn't about finding just another rocky planet in the habitable zone. We've already discovered thousands of those. This is about finding a true twin, a world with a similar size, a stable climate, vast blue oceans, and an atmosphere rich with the telltale biosignatures of life, like oxygen and methane coexisting in an unstable balance that screams something is actively maintaining it. Current and next-generation telescopes are bringing this moment from the realm of fantasy into the crosshairs of science. NASA James Webb Space Telescope is right now analyzing the atmospheres of exoplanets, looking for those chemical fingerprints. And future missions, like the planned Habitable Worlds Observatory, will be designed with one primary goal: to directly image a pale blue dot around another star and scan its light for the definitive evidence of a living world. The scientific impact of such a discovery would be nothing less than revolutionary. For centuries, our models of planetary formation and the emergence of life have been built on a sample size of one, our own solar system. Finding a true analog to Earth would provide the critical second data point, allowing us to finally test which aspects of our world are universal and which are cosmic flukes. Is our mix of nitrogen and oxygen a common recipe for a biosphere, or just one of many possibilities? Does life inevitably lead to a recognizable oxygenated atmosphere? The answers would transform planetary science from a field of informed speculation into a comparative discipline, allowing us to classify worlds and understand the conditions that make a planet truly alive. It would tell us that planets like ours are not rare accidents, but perhaps a common feature in the galaxy. Beyond the raw science, the psychological and philosophical effect on humanity would be profound. For all of recorded history, Earth has been our only example of a living world, a unique jewel in the cosmos. To find another would fundamentally shift our perspective. It would provide a powerful sense of cosmic context, a tangible reminder that we are part of a much larger, living universe. This knowledge could foster a new planetary identity, uniting humanity with the shared realization that we are not the only game in town. It would also provide an immense source of hope, a tangible, reachable destination, a potential second arc for humanity should we ever need it. This world would become a beacon, a guiding star for our future ambitions, physically proving that a long-term, multi-planetary existence is not just possible, but that there are places waiting for us. The discovery would also ignite an unprecedented era of focused exploration. Every available telescope would be trained on this new world, studying its weather patterns, its seasons, and the composition of its continents and oceans. We would relentlessly search for any sign of technology, any artificial signal or atmospheric pollutant that might indicate not just life but intelligence. The mere existence of this planet would become the ultimate rationale for investing in the next great leap in propulsion and spacecraft technology, providing a clear and compelling destination for a centuries-long journey. It would be the answer to the question of why go, made manifest in the heavens, a living, breathing world waiting in the silence of space, inviting us to come and see. For all the promise of life among the stars, our bodies carry a stubborn design flaw. They are irrevocably tied to Earth's gravity. We've seen the toll that long-duration weightlessness takes on even the most elite astronauts, the weakening of bones as they leach calcium, the atrophy of muscles no longer needed to stand or walk, the concerning changes in vision as fluid pressure shifts inside the skull. A trip to Mars could leave explorers so weakened they'd struggle to stand on the red planet's surface, their own bodies turned against them after months in microgravity. This biological barrier represents the single greatest physical obstacle to becoming a spacefaring civilization. But what if we could simply take our gravity with us? The ninth world-changing event is the successful development and implementation of practical artificial gravity, a breakthrough that would transform space from a hostile environment we brave for short periods into a place we can truly call home. The most plausible and elegant solution is one we've seen in science fiction for over a century: rotation. By spinning a spacecraft or a section of a space station, you create centripetal force which pushes objects outward against the interior hull, effectively mimicking gravity. The physics is straightforward, but the engineering is extraordinarily complex. To be both effective and comfortable for human occupants, such a rotating structure needs to be large enough that the difference in gravitational force between an occupant's head and feet is negligible, preventing the disorienting dizziness and nausea that can occur in smaller, faster spinning environments. Imagine a massive rotating hub, perhaps a kilometer or more in diameter, turning at a gentle, imperceptible pace. Inside, the crew would experience a full Earth gravity, allowing them to walk, work, and live normally, their bodies none the wiser that they are hurtling through the void. The immediate benefit would be the preservation of human health on long-duration missions. A crew traveling to Mars inside a rotating habitat would arrive not as weakened patients needing rehabilitation, but as robust, ready explorers, their bones and muscles maintained by the constant, familiar pull of simulated gravity. This eliminates one of the most daunting medical challenges of deep space travel and makes the concept of a permanent colony on a low-gravity world like Mars infinitely more sustainable. Colonists could live in rotating surface habitats that provide an Earth-like environment, periodically venturing out into the native Martian gravity for work and exploration, but always returning to a home that keeps their bodies healthy for a potential return to Earth. This technology would effectively nullify the biological clock that currently ticks against every human in space. Beyond health, the widespread adoption of artificial gravity would be the key that unlocks space for everyone, not just a select few superhumans who can withstand the brutal physiological and psychological stresses of microgravity. It would democratize space travel. With gravity on demand, the journey itself could become as comfortable as a cruise ship voyage. Ordinary people, not just government-trained astronauts, could board a vessel, settle into their gravity-maintained cabins, and travel to orbital hotels, lunar resorts, or even new homes on Mars without undergoing years of intense physical training. This would ignite a true diaspora, turning space colonization from a government-funded exploration program into a human migration, fueled by tourism, industry, and the simple desire for a new life. The solar system would cease to be a frontier only for the exceptionally tough and would become a new neighborhood for humanity. The societal implications of such comfortable, long-term space living are profound. These large, rotating habitats could evolve into entire cities in space, each with their own unique cultures, economies, and ways of life. Some might be dedicated to scientific research in pristine, low-gravity environments, while others could become manufacturing centers for alloys and pharmaceuticals that can only be produced in space. They could serve as way stations and ports for ships traveling throughout the solar system, the bustling interplanetary equivalents of ancient coastal trading cities. By solving the problem of gravity, we wouldn't just be making space safer, we would be laying the foundational technology for the very architecture of an interplanetary civilization, creating the first true homes away from home and ensuring that humanity can not only visit the cosmos but truly live in it. But even as we build the infrastructure for a multi-planetary society, a silent war is being waged in the invisible realm of data and communication. Our modern world, from financial markets to national security, runs on information, and that information is constantly under attack. Current encryption methods, the complex mathematical puzzles that scramble our data, are formidable, but they have a critical weakness. They can be broken by more powerful computers, and the advent of quantum computing threatens to shatter them entirely. This vulnerability could bring our digital civilization to its knees unless we can build a new, unbreakable system. This brings us to the 10th transformative event, the deployment of a global quantum communication network, a web of satellites that would use the bizarre laws of quantum physics to create a new era of perfect, unhackable security. The magic of this system lies in a phenomenon called quantum key distribution. Unlike traditional encryption, which relies on math problems that are just hard to solve, quantum encryption is based on a fundamental law of the universe. The act of observing a quantum system inevitably alters it. Here's how it would work in practice. A satellite in orbit would fire a stream of individual photons or particles of light down to a ground station on Earth. These photons will be prepared in specific quantum states that represent the bits of a digital encryption key. Now, if any eavesdropper tries to intercept this stream of photons to copy the key, their very attempt to measure the particles will disturb their quantum states. This disturbance is instantly detectable as an error in the transmission, alerting both the sender and receiver that the line has been compromised. They would then simply discard that key and generate a new one, making interception not just difficult but fundamentally impossible according to the laws of physics. The implications for global cybersecurity are nothing short of revolutionary. For governments, it would mean that diplomatic cables, military commands, and intelligence sharing could be conducted with absolute certainty of privacy, protecting national secrets in a way never before possible. For the financial sector, it would create an immutable shield around transactions, stock trades, and personal banking data, potentially eliminating digital fraud at its source. Critical infrastructure, power grids, water treatment facilities, and air traffic control systems could be managed through control networks that are immune to remote hijacking, safeguarding society from catastrophic cyber attacks. This wouldn't just be an upgrade to our firewalls, it would be a wholesale replacement of the digital locks and keys that guard our most sensitive information. Establishing this network requires a space-based component because the delicate quantum states of photons can only be preserved over relatively short distances through fiber optic cables on Earth. The atmosphere, however, provides a much clearer path, allowing satellites to act as trusted relays between distant cities and continents. China's MISHA satellite has already demonstrated the stunning feasibility of this technology, successfully performing quantum key distribution between itself and ground stations separated by over 7,000 kilometers, a feat impossible with ground-based technology alone. The next step is to move from a single experimental satellite to a full constellation, a network of quantum nodes in the sky that would create a seamless, global blanket of secure communication. Beyond protecting what we already have, a quantum internet would unlock entirely new capabilities. It could enable perfectly secure online voting, creating a foundation for truly democratic digital elections. It would allow for the private exchange of medical records and genomic data, accelerating personalized medicine without privacy concerns. On a grander scale, linking together future quantum computers through this secure network would create a web of unimaginable processing power, capable of solving problems in medicine, materials science, and climate modeling that are currently far beyond our reach. By taking our cybersecurity to space and harnessing the strange rules of the quantum world, we wouldn't just be preventing disaster, we would be building a new, more trustworthy foundation for the entire next chapter of human progress, one secure photon at a time. But the greatest revolution will be in the realm of medicine. On Earth, gravity causes protein molecules to settle and clump as they crystallize, creating flawed, imperfect structures that are difficult to study. In the persistent free fall of orbit, these same molecules can arrange themselves into pristine, perfectly ordered crystals of a size and quality simply unattainable on our planet. For pharmaceutical researchers, these aren't just beautiful shapes under a microscope, they are the master keys to understanding disease. By analyzing these flawless crystals with X-rays, scientists can map the precise three-dimensional structure of complex proteins, like those involved in cancer or Alzheimer's, with unprecedented clarity. This detailed knowledge allows for the design of new drugs that fit into these protein structures like a key in a lock, enabling the development of hyper-targeted, more effective medications with fewer side effects. We could see the creation of a new generation of wonder drugs, therapies designed with atomic-level precision in the unique laboratory of space. The impact extends to advanced materials as well. Consider fiber optics, the transparent strands of glass that carry the world's internet and phone calls. Their performance is limited by tiny impurities and imperfections that occur during manufacturing in gravity. In microgravity, we could draw flawless glass fibers of unprecedented purity and length, creating a new global network with faster data transmission and significantly less signal loss. The same principle applies to a new class of materials called metamaterials, engineered to possess properties not found in nature. In orbit, we could construct these materials with a perfect, intricate internal structure, potentially creating alloys that are lighter than aluminum but stronger than steel, or ceramics that can withstand the incredible heat of a hypersonic vehicle's skin. The products returning to Earth from these orbital factories wouldn't just be novelties, they would be components that redefine the performance limits of our technology here on the ground. This new industrial paradigm would fundamentally reshape our economy and our relationship with our planet. By offloading the most energy-intensive and polluting manufacturing processes to space, powered by the limitless solar energy available there, we could drastically reduce the environmental footprint of industry on Earth. The terrestrial factories of the future might focus on final assembly using these space-forged wonder materials, leaving the heavy industrial lifting to automated facilities in orbit. This would create a powerful new economic sector, spawning entirely new professions in orbital facility management, space-based quality control, and the complex logistics of transporting raw materials up and finished products down. The first company to successfully manufacture a blockbuster drug or a revolutionary alloy in space will not just earn immense profits, it will open the floodgates to a new economic age, proving that the ultimate factory floor is not on the ground but hanging in the silent, pristine void above us. Our journey through these transformative events has revealed our potential to reshape our future, but there remains a profound and humbling truth. The universe we see, the planets, the stars, the galaxies, all of it is just a fraction of the story. In fact, it's less than 5% of everything that exists. The rest is a complete and utter mystery, a cosmic phantom force we can infer but not see. We call these phantoms dark matter and dark energy, and the 12th event that could change everything is the moment we finally pull back the curtain and directly detect them. This wouldn't just be a new discovery, it would be like humanity finally being given the keys to the universe's hidden operating system, granting us access to fundamental forces and truths we can currently only dream of. For nearly a century, we've known something was missing. When astronomers measured how fast stars orbit the centers of their galaxies, they found they were moving so quickly that the visible matter alone couldn't provide enough gravity to hold them together. The galaxies should have flown apart. The only explanation was that they were embedded in massive, invisible halos of something else, a substance that doesn't emit, absorb, or reflect light, dark matter. Then, at the turn of the millennium, observations of distant supernova delivered an even bigger shock. Not only is the universe expanding, but that expansion is accelerating, as if some repulsive force is pushing space itself apart. This force, dark energy, appears to make up about 70% of the universe's total energy budget. Together, these two dark components govern the cosmos on the largest scales, dictating the fate of galaxies and the ultimate destiny of the universe itself, yet we have no idea what they actually are. Successfully detecting and understanding these entities would represent the greatest scientific revolution since quantum mechanics and relativity. It would unlock a new chapter in physics, one that almost certainly lies beyond our current standard model. The immediate prize for cracking the code of dark matter could be nothing less than control over gravity itself. If we can understand how this invisible substance interacts with the fabric of spacetime to create the gravitational glue holding galaxies together, we might learn to manipulate that interaction. Imagine technology that could generate localized gravitational fields, effectively creating gravity plating for ships or canceling out G-forces for pilots and astronauts. We could move beyond spinning structures for artificial gravity and instead command it directly, turning a fundamental force of nature into a tool we can wield. The implications of mastering dark energy are even more staggering, though far more distant. This energy is woven into the vacuum of space itself, a property of empty nothingness that causes it to push outward. If we could ever learn to manipulate it, even slightly, we would be touching the very mechanism of cosmic expansion. The potential applications border on the realm of magic. Could we create a warp bubble by contracting spacetime in front of a ship and expanding it behind, effectively riding a wave of distorted space to achieve faster than light travel without breaking relativity? Could we stabilize a traversable wormhole by tuning the dark energy at its throat? This knowledge wouldn't just give us the stars, it could give us the entire galaxy, turning the vast, impassable distances between stars into manageable routes. Beyond the promise of unimaginable technology, solving this mystery would answer the most profound questions we can ask about our existence. The nature of dark energy dictates the ultimate fate of all creation. Is its strength constant, leading to a big freeze where the universe expands forever into a cold, dark, and empty eternity? Or does it vary, potentially leading to a cataclysmic big rip that tears apart galaxies, stars, planets, and even atoms themselves in the far future? By pulling these phantoms into the light, we would no longer be speculating about our cosmic destiny. We would be reading it from the universe's own blueprint. This knowledge would complete our cosmological map, finally showing us where the story of the universe is headed, and in doing so, giving us a deeper, more complete understanding of our own humble place within its grand and mostly dark narrative. Now, let's consider a concept that stretches the very fabric of reality itself, one that has been a staple of theoretical physics for over a century but remains just beyond our practical grasp. Einstein's theory of relativity isn't just an abstract idea. It makes a stunning prediction that time itself is not a universal constant. The faster you move through space, the slower you experience time relative to someone who is stationary. This effect, known as time dilation, is minuscule at everyday speeds, but it becomes profound as you approach the velocity of light. For the first human crews embarking on interstellar voyages aboard ships powered by advanced propulsion, this theoretical curiosity would become a breathtaking and potentially unsettling reality. Their journey to the stars would be a one-way ticket not just in space but in time. Imagine a mission to a star system 20 light-years away. Using a propulsion system that allows for continuous acceleration, the ship could reach a significant fraction of light speed. For the astronauts on board, the trip might feel like it only takes a decade due to time dilation. They would live their lives, conduct their research, and raise families born during the voyage, all on a seemingly manageable timeline. But when they finally turn around and return home, they would step out of their ship to an Earth that is 40 years older than when they left. Everyone they knew, parents, siblings, friends, would have aged those full 4 decades, while the crew has only aged 20 years. This isn't science fiction, it's the inescapable math of relativity, and it creates a form of time travel into the future that is absolutely real. The implications of this become even more staggering for longer journeys. A crew traveling to a star 100 light-years away and back could return after a subjective 50-year mission to find that over 2 centuries have passed on Earth. The society they left behind would be almost unrecognizable. The language might have evolved, political borders redrawn, technology transformed, and their own culture become a historical relic. They would be living artifacts, human time capsules from a bygone era, suddenly thrust into a future they helped create but can scarcely understand. This creates a profound psychological chasm between the explorers and the humanity they represent. They would be celebrated as heroes, but also viewed as curiosities, isolated from the very world they risked everything to advance. This temporal disconnect would force us to completely redefine our concepts of mission control and long-term planning. How do you manage a mission when each instruction you send takes years to arrive and the crew's response takes years to return? The chain of command would be broken. The crew would need to be utterly self-sufficient, making critical decisions about their mission, their health, and their society without any hope of real-time guidance from Earth. They would effectively become a new branch of humanity, evolving their own customs, governance, and identity entirely independently during their centuries-long isolation in the void. A round-trip interstellar mission is less like sending a Navy ship across an ocean, and more like launching a new civilization on a journey that will outlast the nation that built it. On a societal level, this raises enormous ethical questions about connection and responsibility. Would the crew even want to return to an Earth that is no longer their home? Would they choose to remain in orbit as observers of the new world, transmitting their invaluable data but refusing to land, becoming permanent exiles from their own time? And what of the people on Earth? How would we handle the emotional burden of saying goodbye to loved ones, knowing we will never see them again in our lifetime, while they will potentially see us again as aged strangers? The very act of sending out interstellar arcs would be an act of incredible sacrifice, creating a permanent separation not just by distance, but by the irreversible river of time itself. Mastering near-light-speed travel would grant us the stars, but it would also force upon us a new and poignant understanding of loss, legacy, and what it truly means to be a part of the human story. And while these grand voyages through time and space capture our imagination, the first practical step toward making them a reality begins much closer to home. Right now, an international race is underway not just to return humans to the moon, but to stay there. The goal is the establishment of a permanent, self-sustaining lunar base, an outpost that does more than just plant flags. It pays its own way by unlocking the moon's vast resources. This isn't about recreating the Apollo campsites. It's about building the first true infrastructure beyond Earth, a project that will transform our barren neighbor into the most valuable piece of celestial real estate in the solar system. The linchpin of this entire endeavor is water. For decades, we believed the moon was a completely dry, desiccated world. But recent missions have revealed a stunning truth. Hidden in the permanently shadowed craters at the lunar poles, trapped in the soil as ice, are billions of gallons of water. This discovery changes everything. Through a process called electrolysis, this water can be split into its 2 basic components, hydrogen and oxygen. Oxygen is, of course, vital for astronauts to breathe, but together, these elements form the most powerful chemical rocket propellant known. liquid hydrogen and liquid oxygen. This means the moon isn't just a destination, it's a propellant depot. A spacecraft launching from Earth on a mission to Mars barely has enough fuel to escape our planet's gravity and begin its journey. But if it could launch with mostly empty tanks, rendezvous with a lunar station, and refuel using locally produced propellant, the entire equation flips. The cost and mass of launching from Earth plummet because you're no longer having to haul all the fuel for the entire trip out of our deep gravity well. The moon becomes a cosmic gas station, enabling cheaper and far more frequent missions into deep space. This resource utilization extends far beyond fuel. The lunar soil itself, known as regolith, is rich in raw materials. 3D printers using sunlight for power and regolith as their ink could be used to fabricate everything from landing pads and radiation shields to entire habitat structures, layer by layer. This approach, called in situ resource utilization, or ISRU, is the ultimate form of living off the land. Instead of spending billions to launch every nut, bolt, and wall panel from Earth, we can use what's already there. A lunar base would become a construction yard, building and assembling the components for larger ships that would be impossibly expensive to launch from Earth in one piece. Imagine massive, rotating habitats for artificial gravity or generation ships for interstellar travel, constructed in the moon's low gravity and devoid of an atmosphere, then launched into space with relative ease. The establishment of such a base would ignite a new economic model in space. It would create a sustainable loop where lunar resources fuel further exploration, which in turn funds more infrastructure. This could spark the first off-world gold rush, not for precious metals, but for the most precious commodity in space, convenience and capability. Nations and private companies would compete to provide services, from offering the most reliable refueling to operating the most efficient regolith processing plants. This activity would drive down costs for everyone and accelerate the pace of exploration, creating a virtuous cycle of investment and innovation. The lunar base would serve as a classroom and a testbed, a place where we learn the critical skills of long-term survival and industry in an alien environment, lessons that are absolutely essential before we can ever hope to establish a foothold on the far more distant and hostile Mars. Ultimately, this first permanent outpost represents a fundamental shift in our philosophy. We are no longer just visiting space, we are learning to inhabit it. We are moving from being explorers to being settlers, from being tenants to being homeowners in the cosmos. The success of this lunar base would prove that humanity can not only survive but truly thrive beyond the cradle of Earth, using the resources of the solar system to fuel our boundless ambition. It would become the foundational node in a growing network of human presence, the first and most crucial stepping stone from which all future journeys to the planets and the stars will leap. But what if the solution to our most pressing planetary crisis wasn't found on Earth at all, but in the space just above it? This brings us to one of the most ambitious and ethically fraught concepts on our list: space-based climate engineering. Imagine constructing a vast, delicate sunshade positioned at the Lagrange point between the Earth and the Sun, a stable gravitational parking spot where it could persistently filter a small percentage of incoming solar radiation. Alternatively, we could deploy a fleet of mirrors or a cloud of dust-sized particles to achieve a similar effect. This isn't about reducing carbon emissions here on the ground. It's about installing a global thermostat in orbit, giving humanity the unprecedented ability to directly dial down the planet's temperature. The sheer scale of such an undertaking is almost beyond comprehension. To have a measurable impact, a solar shield would need to be roughly the size of a small country, spanning millions of square kilometers. Constructing and launching such a structure from Earth is currently impossible. The only feasible way to build it would be to use in situ resources, likely from the moon or asteroids, processed and assembled by autonomous factories in space. This would require the full maturation of the space economy we've previously discussed, turning a geoengineering megaproject into the ultimate driver for off-world industry. The technological leap required is monumental, but the potential payoff is equally staggering. A tool that could rapidly cool the planet, potentially halting the most catastrophic effects of climate change within years rather than the centuries it might take for natural processes to rebalance the atmosphere. Yet, wielding this power responsibly presents a minefield of ethical and geopolitical dilemmas unlike any we have ever faced. Who gets to control the thermostat for the entire world? A single nation or corporation could hold the power to plunge regions into famine by altering rainfall patterns, or to freeze out rivals by redirecting storms. The potential for coercion and climate warfare is terrifying. Even with the most benevolent international oversight, the unintended consequences could be severe. Artificially cooling the planet by blocking sunlight does nothing to address the root cause, the dangerous buildup of carbon dioxide in our oceans and atmosphere. This excess CO2 would continue to acidify the oceans, threatening the entire marine food web. We might save the glaciers from melting only to kill the coral reefs and plankton, the very foundation of oceanic life. We would be treating a fever without curing the disease, creating a fragile and potentially catastrophic dependency on a technological fix that could fail. The greatest danger might be a psychological one, a phenomenon known as moral hazard. The mere existence of a potential technological escape hatch could severely undermine the global political will to do the difficult but essential work of transitioning to clean energy and restoring natural ecosystems. If we believe a silver bullet is waiting in orbit, why make the sacrifices needed to reduce emissions today? This could lead to a future where we are permanently locked into maintaining our orbital sunshade, forever fearful of what would happen if it ever failed or if a future conflict led to it being weaponized. The decision to deploy such a system is not merely a technical one, it is a profound philosophical crossroads. It forces us to ask if we are responsible enough to manage an entire planet's climate, and whether using a grand technological intervention to solve a problem created by our own technology is a display of ultimate wisdom or the height of hubris. Yet for all the grandeur of our own universe, a revolutionary idea has begun to take hold in the minds of cosmologists. What if our cosmos is not unique? What if the Big Bang was not a singular Genesis event, but merely one birth among countless others in an infinite meta-reality? This brings us to the 16th event, the discovery of hard, observational evidence for parallel universes. We are not talking about the science fiction trope of hopping into an alternate reality where you might meet a version of yourself with a different haircut. We are talking about a fundamental rewriting of cosmology where our entire universe, with its hundreds of billions of galaxies, is reduced to a single bubble in a vast, frothing ocean of cosmic foam. The search for this evidence is already underway, focused on the oldest light we can see, the cosmic microwave background, or CMB. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, is the ultimate cosmic fingerprint. Scientists are meticulously analyzing this map for anomalies that the standard model of cosmology cannot explain. Some theories suggest that if our universe collided with a neighboring universe in the distant past, it would have left a peculiar, imprinted pattern in the CMB, a kind of cosmic bruise. Another potential signature could be a mysterious cold spot, a strangely large and cool region in the background radiation that some physicists propose could be the imprint of a gravitational tug from a parallel universe. Finding such a signal would be the smoking gun, the first tangible clue that our reality is not all there is. The philosophical implications of such a discovery would be the most profound in human history, dwarfing even the Copernican revolution. It would mean that the physical laws we consider absolute and immutable, the strength of gravity, the mass of an electron, the very speed of light, are not universal constants at all. They might simply be the local bylaws of our particular cosmic bubble, the outcome of a random roll of the dice when our universe inflated into existence. In other cosmic bubbles, the laws of physics could be completely different. In some, gravity might be so strong that universes collapse instantly back into singularity. In others, the nuclear forces might be too weak to ever form atoms, preventing stars or planets from ever coalescing. We would have to accept that our universe is not fine-tuned for life. Rather, we are a life form that is fine-tuned to exist in this specific universe, one that just happened to have the right recipe to make our existence possible. This realization would force a radical humility upon science and philosophy alike. Every fundamental question about why our universe is the way it is would receive a deeply unsettling answer. It is this way by accident. There is no deeper reason why the constants of nature have the values they do. We just happen to inhabit one of the perhaps rare universes where those values allow for galaxies, planets, and conscious beings to ponder them. This anthropic principle would shift from a philosophical curiosity to a central pillar of our understanding of reality. The search for a single, elegant theory of everything that explains all the forces of nature might need to be abandoned, or at least reframed as a theory that only explains the local rules of our particular cosmic neighborhood. On a human level, this knowledge would be simultaneously liberating and terrifying. It liberates us from the idea that our universe is somehow special or central, completing a journey of cosmic demotion that began with Copernicus. But it is terrifying in its sheer existential scale. Our struggles, our triumphs, our entire history, all of it would be contained within one bubble in an infinite multiverse, rendering our narrative both infinitely precious and cosmically insignificant. The discovery of parallel universes would not give us a technology to wield or a new world to inhabit. Instead, it would give us the ultimate perspective, a cosmic context so vast that it would forever change how we view our place in the grand scheme of existence, challenging every story we have ever told ourselves about why we are here. Yet the idea of sending human-made probes to even a handful of stars pales in comparison to the staggering potential of a single, self-perpetuating mission. Imagine launching just one robotic craft, but one endowed with a singular, transformative ability, the power to create perfect copies of itself. This is the concept of a von Neumann probe, a self-replicating automaton designed to travel to a distant star system where it would mine local asteroids and moons for raw materials. Using these resources, it would then build a factory to construct two identical copies of itself. These two new probes would then travel to two new star systems and repeat the process. This simple act of replication would trigger an exponential wave of exploration, a wave that could wash across the entire Milky Way galaxy in a surprisingly short cosmic timescale. The math behind this is nothing short of breathtaking. If each probe takes 1,000 years to travel to a new system and another 1,000 years to mine, build, and replicate, the process would double the number of probes every 2,000 years. Starting from just one, it would take only about 30 doubling periods to reach over 1 billion probes. That's 60,000 years, a mere blink of an eye in galactic terms. Within a few million years, a time span shorter than the one it took for humanity to evolve from our earliest ancestors, a swarm of these probes could have visited or passed through every single one of the hundreds of billions of star systems in our galaxy. This isn't just exploration, it's the ultimate form of cosmic manifest destiny, executed not by biological beings limited by lifetimes and generations, but by immortal machines that multiply like a virus spreading through the stars. The scientific return from such a project would be beyond comprehension. Each probe would be a sophisticated laboratory equipped to analyze its destination system in minute detail. It would map planets, analyze atmospheres, scour surfaces for signs of geology or biology, and catalog the chemical makeup of asteroids and comets. The data collected will be transmitted back to a network of receivers in our solar system, building into a living, breathing, and endlessly updating Encyclopedia Galactica. We would have real-time data on the climate of an Earth like world-orbiting Proxima Centauri, the mineral composition of a metallic asteroid in the Orion Arm, and the atmospheric spectra of a gas giant in the outer reaches of the galaxy. This constant stream of information would answer nearly every question we have about the frequency of planets, the diversity of solar systems, and the distribution of life throughout the cosmos. Beyond mere observation, these probes could become the gardeners of the galaxy, engaging in a practice known as directed panspermia. Each probe could carry tiny capsules filled with genetically engineered, resilient microorganisms or the raw biochemical precursors of life as we know it. Upon finding a promising young world with liquid water and a stable climate, but no signs of native life, a probe could seed these oceans, effectively planting the flag of Earth's biosphere on a new world. Over millions of years, this could lead to the spontaneous emergence of life based on our own biochemistry, effectively spreading a branch of Earth's tree of life across the cosmos. Humanity would become a silent, indirect creator of worlds, fostering life on a galactic scale long after our own species may have evolved or disappeared. Yet, this godlike power comes with profound and sobering responsibilities. The same technology that could be used for peaceful exploration and cosmic gardening could also be weaponized into an unstoppable force of destruction. A probe programmed for disassembly rather than construction could become a berserker, a robotic plague designed to strip entire star systems of resources to fuel its own replication, systematically dismantling planets and moons and leaving behind a trail of sterile rubble. The ethical dilemma of directed panspermia is equally complex. Would we have the right to seed a world that might have given rise to its own unique, nascent biology given another few million years? We might inadvertently extinguish a truly alien genesis of life before it even had a chance to begin, replacing it with our own terrestrial model and forever reducing the potential diversity of life in the universe. The development of the von Neumann probe is not just a technological milestone, it is a test of our species' maturity, demanding that we carefully consider whether our legacy to the galaxy will be one of enlightened curiosity or reckless, exponential consumption. What if the greatest archaeological find in human history isn't buried in the sands of Egypt or hidden deep within a jungle, but is instead drifting silently in the cold, dark reaches of our own solar system? We are talking about the detection of precursor alien artifacts, objects of unmistakably artificial origin that were not made by us. This isn't about receiving a message, it's about discovering a tool, a piece of technology left behind by a civilization that may have passed through our neighborhood eons before humans even walked the Earth. Such an artifact could be resting on the sterile surface of a moon like Callisto, tumbling through the asteroid belt, or parked in a stable orbit around a gas giant, waiting patiently in the ultimate time capsule for a species curious enough to find it. The discovery would begin not with a dramatic signal but with a puzzling anomaly. A planetary survey probe mapping the surface of a distant moon would transmit images of something that defies all natural geology, a structure of impossible geometry, made of a material with spectral signatures unlike any known element or alloy. The immediate, heart-stopping realization would be that we are looking at something built. The following months would be a whirlwind of frantic activity, as every available telescope is trained on the object and a dedicated mission is scrambled to investigate it up close. The world would hold its breath as a new spacecraft, likely a repurposed orbiter with a lander component, makes the long journey to rendezvous with this silent sentinel from the stars. Upon arrival, the true magnitude of the find would unfold. This wouldn't be a simple monument. The greatest hope is that it would be functional, a piece of technology preserved in the perfect vacuum of space. Imagine a device that demonstrates a principle of physics we have only theorized, like a working gravity generator or a compact energy source tapping directly into zero-point energy. It might contain a material that acts as a perfect room temperature superconductor, or a data storage medium of such density and durability that it has held information for millions of years. The artifact would be a black box from an alien engineering culture, a physical tutorial offering solutions to problems that have plagued our scientists for decades. The impact on human technology would be a quantum leap unlike any other. Instead of the slow, painstaking process of incremental scientific progress, we would be handed the answers. It would be like giving a smartphone to a Renaissance inventor. We could reverse engineer the principles behind this technology, leapfrogging past centuries of research and development. The energy crisis could be solved overnight if we could decipher and replicate its power source. Material science would be revolutionized by alloys with unheard-of strength-to-weight ratios. Our entire understanding of propulsion could be rewritten, slashing travel times across the solar system from years to months and bringing interstellar voyages into the realm of possibility for the first time. This one object could single-handedly launch a new technological renaissance, catapulting our civilization forward by thousands of years. Yet, with this incredible gift would come profound and unsettling questions. Why is it here? Was it left as a deliberate beacon for emerging species, a sort of cosmic welcome package intended to accelerate our development? Or is it merely discarded junk, the equivalent of an ancient alien soda can littering the cosmic roadside? The more ominous possibility is that it is a monitor, a passive observatory that has been quietly studying our planet and its evolution for millennia, its discovery now triggering an alert to its creators that we have finally reached a level of maturity worthy of their attention. The artifact itself may be benign, but the civilization that made it might not be. Finding such an object would force us to confront the reality that we are no longer the masters of our own solar system. We are merely the current tenants, and the previous occupants possessed a technology so advanced it borders on magic. We would have to grow up very quickly, balancing the exhilarating rush of new knowledge with the sobering responsibility that comes with unlocking powers we do not yet fully understand. Now, let's turn our focus from grand cosmic mysteries to a far more immediate and human need, the simple act of feeding ourselves. For our entire history, agriculture has been a planetary endeavor, bound by the constraints of soil, seasons, and weather. But what if we could break free from those limitations, not by finding more land, but by moving our farms entirely off-world? The 19th event on our countdown is the dawn of a true space-based agricultural revolution, where orbital farms growing food under the constant sun and in the absence of gravity could solve some of our oldest and most persistent challenges. Picture a facility not unlike the International Space Station, but dedicated solely to plant life. Inside, instead of traditional soil, plants would grow aeroponically, their roots misted with a perfectly balanced nutrient solution, or hydroponically, suspended in a water-based solution rich in everything they need. Here, there is no gravity to dictate the flow of fluids, so plants grow in a state of constant, stress-free abundance, with water and nutrients delivered directly to their roots with impossible efficiency. Every aspect of the environment is meticulously controlled: carbon dioxide levels, humidity, temperature, and most importantly, light. With no atmosphere to filter it, pure, intense sunlight is captured and then delivered to the plants via banks of specially tuned LEDs, providing each species with the exact spectrum of light it needs for optimal growth, 24 hours a day, 365 days a year. There are no pests, so no pesticides are needed. There are no droughts, no floods, no unseasonable frosts. This is agriculture perfected, reduced to its most efficient and productive form. The potential breakthroughs from such a controlled environment are staggering. Scientists have already observed that the stress of microgravity can cause plants to express genes differently, sometimes leading to accelerated growth rates or higher concentrations of vitamins and antioxidants. By carefully manipulating these conditions, we could essentially bioengineer without genetic modification, creating super nutritious crops designed to combat malnutrition. Imagine a strain of lettuce grown in orbit that contains twice the vitamin C of its earthly counterpart, or tomatoes packed with enhanced levels of cancer-fighting lycopene. This isn't just about producing more food, it's about producing better food, turning every leaf and fruit into a potent, natural supplement tailored for human health. The research conducted in these orbital labs would also provide invaluable data to improve terrestrial farming, teaching us how to achieve higher yields with less water and fewer chemicals back on Earth. The most immediate and critical application of this technology is the key to unlocking the solar system. For any long-duration mission, be it to Mars or beyond, the ability to be self-sufficient is everything. Shipping all the necessary calories from Earth is monumentally expensive and incredibly risky. A single supply chain failure could doom a mission, but a spaceship or planetary base with its own integrated bio-regenerative life support system changes everything. Plants would do more than just provide fresh, nutritious food. They would be the lungs of the habitat, absorbing the carbon dioxide exhaled by the crew and replenishing the oxygen through photosynthesis. They would purify water through transpiration, with the moisture they release being captured and recycled. This creates a closed-loop ecosystem, a tiny, self-sustaining arc where humans and plants support each other in a perfect balance. This is not a luxury, it is an absolute necessity for the long-term survival of any off-world colony, turning a distant outpost from a precarious camp into a true home. Back on Earth, the implications for global food security are equally transformative. While it may never be economical to ship lettuce from orbit to your local supermarket, the technologies perfected there will be. Vertical farming here on Earth, inspired and optimized by space-based research, could see a massive expansion. Vast multi-story facilities in urban centers, using the same precise LED lighting and soil-free growing techniques, could produce enormous quantities of food right where the majority of people live, drastically reducing the environmental cost of transportation and traditional agriculture. These indoor farms are immune to climate change, capable of producing harvests year-round regardless of the weather outside. For regions afflicted by famine or with non-arable land, mobile, container-sized versions of these systems could provide a lifeline, a reliable source of fresh produce where it was once impossible. The space agriculture revolution wouldn't just feed astronauts. Its technological offspring could be the tool we use to finally end hunger on our own planet, making the dream of abundance a practical, achievable reality for everyone. But our journey through the cosmos has so far been constrained by the speed of light, a universal speed limit that makes the vastness of the galaxy feel like an impenetrable barrier. What if the universe itself provided a way to cheat? This brings us to one of the most fantastical yet theoretically possible structures ever proposed: cosmic strings. These are not strings in any ordinary sense, but incredibly thin, unimaginably dense defects in the fabric of spacetime itself, theoretical remnants from the universe's first moments of existence after the Big Bang. Think of the early cosmos as a cooling liquid. As it underwent profound phase transitions, cracks and fissures might have formed in the very structure of reality, and these one-dimensional cracks are what physicists call cosmic strings. A single centimeter of one of these strings could contain more mass than all the mountains on Earth combined, warping space-time around it with incredible intensity. The mere discovery of such an object would be a monumental validation of our theories about the birth of the universe, but its potential utility is what truly sparks the imagination. Due to their immense mass and the extreme curvature of spacetime they create, two cosmic strings moving past each other at high speed could create a closed time-like curve, a pathway that loops back on itself in time. This theoretically opens the door to something even more incredible than faster-than-light travel, actual time travel into the past. While the engineering challenges of harnessing such a phenomenon are far beyond our current comprehension, the simple confirmation that these structures exist and possess these properties would fundamentally change our perspective on what is possible in the universe. It would transform time travel from a science fiction trope into a theoretical physics problem waiting to be solved. Perhaps a more immediate application lies in their use as cosmic superhighways. The tremendous gravitational pull of a cosmic string could be used as a slingshot of unimaginable power. A spacecraft could use a carefully calculated trajectory to swing around a string, stealing a fraction of its immense orbital energy to achieve velocities a significant fraction of the speed of light without needing to carry any propellant. This would turn these strings into natural accelerators scattered throughout the galaxy, waypoints on an interstellar travel network that could make journeys to nearby stars a matter of years instead of millennia. Mapping the locations of these strings would become the most important astrometric project in human history, the first step in charting a practical course for human expansion beyond our local stellar neighborhood. The existence of cosmic strings would also suggest that other, even stranger topological defects might be real. Concepts like wormholes, often visualized as tunnels connecting distant points in spacetime, might be stable only if lined by a form of exotic matter with negative energy density. Some theories suggest the cores of cosmic strings or similar structures could contain such matter, providing a potential blueprint for creating or stabilizing these shortcuts artificially. Finding a cosmic string would not just be about finding one tool. It would be like finding the master key to a whole new toolbox of cosmological engineering, offering hints on how to manipulate the fabric of spacetime itself. This knowledge would push humanity from being mere passengers in the universe to potential pilots, giving us access to realms of reality we currently believe are forever locked away by the fundamental laws of physics. And now we arrive at a power source so potent, so theoretically perfect, that it has been the dream of physicists and science fiction writers for generations. We are talking about the holy grail of propulsion, matter-antimatter annihilation. To understand its staggering potential, you first have to appreciate the fundamental inefficiency of every rocket we've ever built. Chemical rockets, like those that took us to the moon, are incredibly wasteful. They burn massive amounts of fuel just to throw a tiny fraction of that fuel backward to generate thrust. Even advanced nuclear propulsion systems only tap into a small percentage of the energy stored inside atomic nuclei. But matter-antimatter annihilation is in an entirely different league. It is the 100% efficient conversion of mass directly into energy, following Einstein's most famous equation, E equals mc squared. When a particle of matter meets its antimatter counterpart, they obliterate each other in a flash of pure energy, releasing 1 billion times more energy per kilogram than chemical combustion. Harnessing this cosmic fire would be like moving from a campfire to a supernova in a single technological leap. The implications for interstellar travel are nothing short of revolutionary. With this kind of energy density, a spacecraft could accelerate to a significant fraction of the speed of light, 50, 70, even 90%. At those velocities, the galaxy suddenly shrinks from an impossible vastness to a network of reachable destinations. A journey to our nearest stellar neighbor, Proxima Centauri, which would take tens of thousands of years with today's technology, could be reduced to a voyage of just a few years from the perspective of the ship. Even more distant, promising star systems like TRAPPIST-1, with its multiple Earth-sized planets, or the tantalizingly habitable zone around the star Tau SETI, would transition from subjects of telescopic study to tangible destinations for human crews. This propulsion system wouldn't just make interstellar travel possible. It would make it practical, compressing journeys that span generations into missions that could be completed within a single human lifetime, completely reshaping our concept of what exploration means. The engineering challenges, however, are as immense as the rewards. Antimatter is the most elusive and expensive substance ever produced by humans. We can only create tiny amounts, a few atoms at a time, in massive particle accelerators like CERN, and it costs hundreds of billions of dollars to produce just a single gram. Then comes the problem of storage. Antimatter annihilates on contact with any matter, so it must be held in a perfect vacuum within magnetic fields of incredible precision, a feat akin to storing a lightning bolt in a bottle. Any failure, any minute fluctuation in the magnetic containment field would result in a catastrophic explosion, making the spacecraft itself the most powerful bomb ever conceived. The development of this technology would require breakthroughs in energy production, materials science, and magnetic confinement that we can scarcely imagine today, pushing human ingenuity to its absolute limit. Yet the pursuit is worth it because mastering this power would do more than just propel ships. It would fundamentally alter our relationship with the cosmos. The ability to travel between stars within a human lifespan would transform humanity from a species confined to a single solar system into a truly interstellar civilization. We would no longer be sending out lonely, one-way generation ships into the dark. We could establish permanent, two-way trade and communication routes between star systems. This would allow for the exchange of not just resources and information, but of cultures and ideas, creating a diverse, galaxy-spanning tapestry of human experience. Colonies on worlds orbiting other suns would no longer be isolated outposts doomed to divergent evolution, but integral parts of a connected and vibrant interstellar community. The development of matter-antimatter propulsion is the key that unlocks this future, turning the silent, distant points of light in our night sky into the streetlights of a new and boundless human frontier. For most of human history, our view of the cosmos was static and eternal. The stars were fixed in their celestial spheres, and the universe, if it was considered to have a history at all, was thought to be unchanging. That all changed in the 1920s with Edwin Hubble's revolutionary discovery that the galaxies are all rushing away from each other, revealing that the universe is not static but dynamically expanding. This discovery opened a profound line of inquiry that continues today. If the universe is expanding, how will that expansion end? The 20-second event that could change everything is the moment we finally answer that question, using precise measurements to detect the universe's ultimate fate, giving humanity a glimpse of our cosmic expiration date. This isn't abstract philosophy, it's a hard-nosed scientific measurement centered on one crucial number, the Hubble constant. This value describes the rate at which the universe is expanding today. But to predict the future, we need to understand the past and present behavior of the force driving that expansion, dark energy. Is the strength of this mysterious repulsive force constant over time, or is it changing? The answer to this question will determine which of three possible cosmic destinies awaits our universe. Major international projects like the Dark Energy Survey and the upcoming Vera C. Rubin Observatory are dedicated to making these ultra-precise measurements by mapping the distribution of billions of galaxies and studying distant supernova to see how the expansion rate has changed over billions of years. We are essentially taking the universe's vital signs to diagnose its long-term prognosis. The first and currently most favored scenario is known as the heat death or big freeze. In this future, dark energy remains constant, acting as a steady, relentless force. The expansion of the universe continues to accelerate forever. Over trillions of years, galaxies will be pulled so far apart that the night sky from any planet will become utterly black and empty. All stars will eventually burn out, their fuel exhausted. Black holes will slowly evaporate away through Hawking radiation, and the universe will approach a state of absolute zero temperature. In this eternal, frozen darkness, all energy is evenly distributed, no work can be done, and all activity ceases forever. It is a quiet, desolate, and permanent end. The second possibility is the Big Crunch, a dramatic reversal of our current expansion. This would happen if the density of matter and energy in the universe is high enough that gravity eventually overcomes the force of dark energy, putting the brakes on expansion and pulling everything back together. The universe would begin to contract, slowly at first, then with increasing violence. Galaxies would merge in a celestial demolition derby. The background temperature of the universe would skyrocket, and all matter would eventually be compressed into an infinitely hot, dense singularity, a mirror image of the Big Bang. This cyclical model suggests our universe might be just one in an endless series of expansions and contractions, a cosmic heartbeat with each beat lasting hundreds of billions of years. The most violent and strange destiny is the Big Rip. This scenario occurs if dark energy is not constant, but instead grows stronger over time. In this case, the expansion doesn't just accelerate, it becomes exponentially more powerful until it overwhelms every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the force intensifies, solar systems are ripped from their gravitational anchors. In the final terrifying moments, the overpowering expansion would tear planets apart, and then atoms themselves would be shredded, dissolving the very fabric of space-time into a chaotic foam of fundamental particles. It is the most absolute and destructive end imaginable. Knowing which of these fates is ours would have a psychological impact unlike any other scientific discovery. It would be the ultimate context for human existence, framing every ambition, every tragedy, and every triumph against the backdrop of a definitive cosmic timeline. If we discovered a Big Crunch was imminent in, say, 100 billion years, it might instill a sense of cosmic urgency, a drive to ensure that something of our civilization survives to the next cycle. Finding evidence for a Big Rip would be existentially terrifying, but could also foster an incredible appreciation for the fragile, temporary miracle of structure and life in a universe hell-bent on tearing itself to pieces. And if the Big Freeze is confirmed, it presents a profound challenge to find meaning in a universe destined for eternal silence, pushing us to create our own purpose and beauty within the finite time we have. This knowledge would fundamentally reshape our long-term planning as a species. It would move the goalposts of legacy from thousands of years to trillions. If the universe has a finite lifespan, even an incomprehensibly long one, our projects could be geared toward surviving until the very end, perhaps by engineering a migration to a younger universe if such a thing is possible. If the universe is cyclical, we might focus on encoding our knowledge into indestructible monuments that could survive the bounce into the next cosmic iteration, sending a message to the civilizations of the next universe that we were here. This would be the ultimate act of hope, a testament to life's stubborn insistence on leaving a mark, even on the canvas of eternity itself. Determining the universe's fate would be the final piece of our cosmological map, showing us not just where we came from, but the final destination of the incredible journey we are all a part of. But the truly transformative potential of this research lies in the possibility of enhancing humanity itself for life beyond Earth. Our bodies are the product of billions of years of evolution optimized for a very specific set of conditions: Earth's gravity, atmosphere, and radiation shielding. These are handicaps in space. What if we could use the insights gained from microgravity gene editing to correct these evolutionary oversights for an off-world environment? We could potentially engineer astronauts and eventually colonists with a heightened natural resistance to cosmic radiation, perhaps by borrowing DNA repair mechanisms from extremophiles like the nearly indestructible tardigrade. We could enhance bone density and muscle mass at the genetic level to counteract the atrophy of microgravity, creating humans who are naturally robust against the decay of spaceflight. This wouldn't be about creating a separate species, but about offering a toolkit of biological adaptations that allow humanity to thrive in environments we were never meant to inhabit, turning the debilitating challenges of space into manageable aspects of daily life. The most profound and ethically complex application, however, extends beyond human enhancement to the realm of creating entirely new life forms. Astronauts on a future Mars base wouldn't just be growing plants, they could be designing them. Using genetic tools perfected in orbit, they could engineer robust, fast-growing crops specifically tailored to the Martian regolith and low-gravity environment, plants that might look nothing like their earthly ancestors. But why stop at plants? Imagine designing simple microorganisms or even more complex organisms from the ground up to be the literal ecosystem engineers of another world. These synthetic life forms could be released into the Martian environment to slowly process the atmosphere, break down toxic perchlorates in the soil, or establish a foundational layer of a new engineered biosphere. We wouldn't just be adapting life to new worlds, we would be crafting entirely new branches of the tree of life, consciously directing evolution to terraform planets and create habitable spaces out of barren rock. This power to act as creators, not just explorers, would mark a fundamental shift in our relationship with the cosmos, bestowing upon us a responsibility more profound than any we have ever faced. Yet for all the destructive fury of black holes, their very existence in the laws of physics hints at a tantalizing symmetry. If a black hole is a one-way door into a region of space-time from which nothing can return, could there be a corresponding one-way exit? This brings us to one of the most mind-bending possibilities in all of cosmology, the potential discovery of a white hole. In theory, a white hole would be the exact mathematical opposite of a black hole. Instead of an event horizon from which nothing can escape, it would possess a horizon from which nothing can enter. It would be a cosmic gusher, violently expelling matter and energy into the universe in a dazzling, explosive display, while forever refusing to accept anything in return. While no such object has ever been observed, its potential discovery wouldn't just add a new wonder to the celestial menagerie. It would rip open the textbooks of modern physics and force a complete rewrite. The immediate revolutionary impact would be on our understanding of gravity and the fabric of space-time itself. Einstein's theory of general relativity, which perfectly predicts the existence of black holes, is mathematically time-symmetric. This means the equations work just as well if you run time forward or backward. A black hole, from this perspective, is a region of collapsing matter. If you reverse the arrow of time for a black hole, you get its opposite, a region of eternally expanding, exploding matter, a white hole. Finding one would be the first direct observational evidence that this time symmetry isn't just a mathematical curiosity, but an actual feature of the real universe. It would provide a unique laboratory for studying the most extreme gravitational environments, potentially allowing us to see the other side of a gravitational collapse and finally witness what happens to the information that seems to vanish into a black hole's singularity, a paradox that has troubled physicists for decades. This discovery could also shatter our current cosmological timeline. Some leading theories suggest that the Big Bang itself might not have been a singular starting point, but rather the explosive white hole event of a black hole that formed in a parent universe. In this fascinating cosmic natural selection model, every black hole in our universe could potentially spawn a new baby universe in its incredibly compressed interior with its own Big Bang. Our entire cosmos, with its hundreds of billions of galaxies, might simply be the interior of a black hole existing within a much larger meta-universe. The detection of a white hole would provide the first tangible evidence for this extraordinary idea, revealing that our universe is not isolated but is part of a vast, branching multiverse of cosmoses, each with its own unique physical laws born from the collapse of a star in a world beyond our own. Perhaps the most captivating possibility is that a white hole could function as a bridge, one end of an Einstein-Rosen wormhole with a black hole acting as the other. In this scenario, the terrifying singularity at the heart of a black hole might not be a dead end but a tunnel mouth. The white hole would be the exit, potentially located in a different time or a completely different region of spacetime. While the practical challenges of surviving such a journey are beyond any technology we can conceive, the mere existence of such a structure would prove that the universe is fundamentally connected in ways we never dreamed. It would transform the cosmos from a collection of isolated points into a single, intricate network of shortcuts and pathways, a subway system of reality where the stations are stars and the tunnels are woven from the fabric of space-time itself. Finding a white hole would be the ultimate clue that the universe is not just stranger than we imagine, but stranger than we can imagine, filled with wonders that currently exist only on the far frontier of theoretical physics. Imagine a future where reaching orbit is as simple and routine as boarding a high-speed train, a journey that doesn't require a thunderous, explosive rocket launch but a smooth, electric-powered ascent into the sky. This is the promise of the space elevator, a concept that has captivated engineers and dreamers for decades and stands as one of the most transformative infrastructure projects ever conceived. At its heart, the idea is breathtakingly straightforward: a single, incredibly strong cable, or ribbon tethered to a platform on the Earth's equator and extending upward for 36,000 kilometers, terminating at a counterweight in geostationary orbit. Electrically powered climbers would glide up and down this ribbon, carrying cargo and passengers out of our planet's gravity well for a fraction of the current cost and risk. The economic implications of such a structure are nothing short of revolutionary. Today, launching anything into space is an exorbitantly expensive endeavor, with costs averaging around $10,000 per kilogram. This staggering price tag is the primary bottleneck for every ambitious project, from orbital solar farms to large-scale asteroid mining. A functioning space elevator would shatter this barrier, potentially reducing that cost by over 99%, bringing it down to merely hundreds of dollars per kilogram. This isn't just an incremental improvement, it's a complete paradigm shift. Suddenly, the economic model for everything in space flips on its head. Building a large space station would no longer require the complex and risky assembly of dozens of individually launched modules. You could simply send up the raw materials in massive quantities and construct it in orbit with ease. The concept of in-space manufacturing would evolve from a niche experiment into a dominant industry, as factories could be supplied continuously and cheaply. This democratization of access would open the space frontier to virtually everyone. Universities could launch their own satellites for research. Artists could conceive of orbital installations, and entire new industries we can't yet imagine would spring up around cheap mass-to-orbit capabilities. The construction of the elevator itself would be the greatest engineering project in human history, but it would also be the last major obstacle to becoming a true spacefaring civilization. Once completed, it would serve as a permanent gateway, a constant connection between our terrestrial home and the unlimited resources and possibilities of the solar system. The sheer volume of material that could be lifted would make previously fantastical projects like large-scale orbital habitats, interplanetary spacecraft, and massive solar power satellites not just feasible but economically viable. The key to turning this vision into reality lies in a single, miraculous material: carbon nanotubes. This is the technology that makes the concept theoretically possible. A space elevator ribbon must be incredibly strong and incredibly light, with a tensile strength far beyond any conventional metal or alloy. Carbon nanotubes, with their unique molecular structure, possess this theoretical strength. The challenge, which has been the primary hurdle for decades, is manufacturing them at the required macroscopic scale and perfect quality, without the microscopic flaws that would cause the entire structure to fail under its own immense tension. A global race is underway in materials science labs to crack this code. The moment we achieve the ability to produce continuous, flawless strands of carbon nanotubes kilometers in length, will be the signal that the space age is truly beginning, marking the start of a construction project that would unite the world in a common goal and redefine our future as a species. Yet for all our mapping of cosmic structures and forces, a more profound and unsettling question remains. What if the universe is not just a physical system, but a mental one? This brings us to the 26th event, a possibility so radical it challenges the very foundation of material science, the detection of evidence suggesting the universe itself possesses a form of consciousness. This isn't about finding a god in the classical sense, but rather uncovering through advanced physics and cosmology that awareness might be a fundamental property of the cosmos, as intrinsic to reality as space and time. Imagine our most powerful telescopes and sensors designed to probe the deepest laws of physics, returning data that cannot be explained by blind, mechanistic processes alone. Perhaps we find that the fundamental constants of nature are not randomly set, but appear to be actively maintained in a state of perfect balance, as if being observed. Or maybe quantum entanglement, the mysterious connection between particles across vast distances, behaves in ways that suggest a universal field of information exchange resembling a primitive form of thought. These wouldn't be signals from an alien intelligence within the universe, but clues that the universe itself is the intelligence. The roots of this idea stretch back to the very birth of quantum mechanics. When the pioneers of the field, like Niels Bohr and Werner Heisenberg, discovered that the act of observation by a conscious mind seemed to collapse a particle's probability wave into a fixed state, it introduced a profound puzzle. Is consciousness required to complete reality? This interpretation, known as the Copenhagen interpretation, has been debated for a century, often sidelined as a philosophical oddity. But what if future experiments could no longer dismiss it? Consider an advanced version of the double-slit experiment, conducted on a macroscopic scale. If we were to send complex molecules or even viruses through a double-slit apparatus and found that their wave-like behavior only collapsed when registered by a conscious observer, and not merely by a non-conscious measuring device, it would provide stunning empirical weight to the idea that mind and cosmos are inextricably linked. This would suggest that awareness is not an emergent property of complex brains, but a basic feature of existence that brains merely tap into and amplify. The implications of such a discovery would trigger the most profound paradigm shift in human history, dwarfing the Copernican and Darwinian revolutions combined. Our entire scientific framework is built on the assumption of an objective, external reality that exists independently of anyone observing it. If that foundation crumbled, we would need to construct a new science, one that incorporates consciousness as a fundamental variable in its equations. This wouldn't invalidate physics, it would complete it, finally bridging the chasm between the objective world of atoms and the subjective world of experience. The hard problem of consciousness, why and how physical processes in the brain give rise to subjective experience, would be turned on its head. The brain wouldn't generate consciousness, it would be a receiver or a filter for a consciousness that is already everywhere, a localized whirlpool in a vast cosmic ocean of mind. This new cosmology would force a dramatic reconciliation between science and spirituality. The age-old concept of panpsychism, the view that mind is a ubiquitous feature of all matter, would move from the fringe to the forefront of scientific inquiry. We might begin to see the universe not as a cold, empty machine, but as a living, thinking entity in a state of perpetual becoming, with galaxies and stars acting as neurons in a neural network of unimaginable scale. The purpose of human existence would be cast in a new light. Instead of being accidental, temporary flickers of awareness in a meaningless void, we could be the universe's way of becoming aware of itself, localized points where the cosmos reflects upon its own beauty, complexity, and wonder. Our art, our science, our love, and our curiosity would no longer be quaint human hobbies. They would be the universe celebrating and exploring its own existence through us. Navigating this new reality would present immense practical and ethical challenges. If consciousness is fundamental, then the ethical consideration we extend to other beings might need to be expanded to encompass all of nature. Does a river have experiences? Does a planet? This could give rise to a new cosmic-scale ethic of respect for the processes of the universe itself. Furthermore, if the universe is in some sense aware, then our attempts to understand it through science become a form of communication. Every experiment is a question we pose, and every result is the universe's answer. This transforms the scientific endeavor from a process of dissection into a dialogue, a collaborative unfolding of meaning between humanity and a conscious cosmos. The detection of a universal consciousness would not provide final answers, but it would open the door to a new kind of relationship with reality, one based on participation and reverence rather than domination and extraction, forever altering our journey from lonely observers to active, conscious participants in a waking universe. Yet as we extend our reach across the solar system, our probes and rovers might uncover a truth far more humbling than any empty universe: the possibility that we are not the first. Imagine a future mission, perhaps a drone flying through the thick, acidic clouds of Venus, using advanced LiDAR to map the surface beneath the perpetual haze. The data returns revealing not just ancient volcanoes, but the stark, geometric outlines of a vast, buried metropolis, its structures eroded by acid rain but unmistakably artificial. Or picture a Martian rover tasked with collecting samples from the deep subsurface, whose drill instead strikes not rock but a smooth, manufactured panel, covered in incomprehensible glyphs and sealed for 1 billion years. This is the 27th event, the discovery that intelligent, technological life did not just arise once on Earth, but flourished right next door, only to vanish long before the first dinosaurs walked our world. The immediate scientific impact would be a complete rewriting of our planetary history. We currently view places like Mars and Venus through a purely geological lens. Mars as a cold, dead world that may have once had simple life, and Venus as a scorching example of a runaway greenhouse effect. Finding the ruins of a civilization on either would force us to see them as failed biospheres, worlds that nurtured life to its highest potential only to have it snuffed out by catastrophic change. The question would instantly shift from "are we alone?" to "what happened to them?" Planetary scientists would become cosmic forensic detectives, piecing together the clues of their demise. Did the Martians perish when their planet lost its magnetic field and atmosphere was stripped away by the solar wind? Did the Venusians trigger their own apocalypse through unchecked climate change, turning a temperate world into a hellish pressure cooker? Their fate would serve as the ultimate cautionary tale, a stark monument to the fragility of all civilizations, no matter how advanced. This discovery would force a dramatic re-evaluation of our own place in cosmic history. The entire timeline of intelligence on Earth, from the first tool using hominids to our modern technological era, spans a mere 3 million years, a blink of an eye in the 4.5 billion year history of our planet. If a civilization rose and fell on Mars 1 billion years ago, when Earth was inhabited only by single-celled organisms, it would reveal a terrifying truth: that the universe has likely been creating and destroying intelligent life for eons, with humanity being merely the latest experiment, not the main event. We would have to confront the sobering likelihood that greatness and extinction are two sides of the same coin, and that the silence we hear from the cosmos isn't because no one is out there, but because no one lasts for long. The most profound shock, however, would come from the potential for knowledge transfer. Within those ruins could lie the equivalent of a cosmic library, a record of a science and technology that developed along a completely different path than our own. They might have mastered forms of energy, materials, or computing that we haven't even dreamed of. Deciphering their knowledge could catapult our own civilization forward by thousands of years, offering solutions to disease, energy scarcity, and existential threats. But it could also contain warnings. Perhaps they left behind a monument not to celebrate their achievements, but to mourn their hubris, a message carved in stone for any species that follows. This is how we fell. Do not make the same mistakes. Their legacy would be the most valuable inheritance imaginable, a guidebook for survival written in the ashes of a dead world, granting us the priceless gift of learning from someone else's extinction rather than our own. But for all the potential of antimatter rockets and cosmic superhighways, they still rely on moving a physical vessel through the void, a process that takes time, no matter how short we make it. What if we could skip the journey entirely? What if we could simply disappear from one location and reappear in another instantaneously? This brings us to the 28th event, a concept that lives at the very edge of science, the development of practical teleportation. We are not talking about the sci-fi trope of a machine that disassembles you in one place and reassembles a copy elsewhere. We are talking about a technology rooted in the bizarre, non-local connections of quantum physics, a technology that could make distance itself obsolete. The foundation for this incredible possibility is being laid right now in laboratories around the world, and it all hinges on a phenomenon called quantum entanglement. This is the deeply strange process where two particles become linked or entangled, such that the quantum state of one instantly influences the state of the other, no matter how far apart they are separated. It's as if you had two magical coins. You flip one in New York and it comes up heads, and you know without any delay that its entangled partner coin in Tokyo has simultaneously become tails. This spooky action at a distance, as Einstein called it, violates our classical intuition about how the universe should work, but it has been demonstrated repeatedly in experiments. The current application for this is in quantum communication, creating perfectly secure encryption keys, as we discussed earlier. But the next step is quantum teleportation, which is the transfer of the quantum state of a particle, its unique identity, from one location to another using an entangled pair as a channel. Performing these incredibly delicate experiments on Earth is extraordinarily difficult because the fragile entangled state is easily destroyed by interactions with the environment, a process called decoherence. This is where the perfect, persistent vacuum of space becomes the ultimate laboratory. In orbit, far from the vibrations, the atmosphere, and the magnetic fields of Earth, we could create and maintain large-scale arrays of entangled particles with much greater stability and over much longer distances. A space-based quantum laboratory could perfect the process of teleporting the quantum states of individual atoms, then molecules, and perhaps one day, far in the future, something vastly more complex. This wouldn't be about moving physical matter, it would be about moving information, the precise quantum blueprint of an object across vast distances to be reconstructed at the other end. Imagine a future where a space station orbiting Mars maintains a vast pattern buffer of raw material atoms of carbon, hydrogen, oxygen, nitrogen, all the fundamental building blocks of life and machinery. On Earth, an incredibly powerful scanner would map the exact quantum state of an object or a person, a process that would effectively disassemble the original into its constituent particles. That quantum information would then be instantaneously transmitted via a protected entangled link to the Mars station, where it would be used to instruct assembler machines to reconstruct the object or person from the local raw materials, atom by atom. From the perspective of the person stepping into the scanner on Earth, they would close their eyes and open them a moment later on Mars, having effectively traveled the hundreds of millions of kilometers between worlds in the time it takes to blink. The implications for colonization and exploration are breathtaking. Instantaneous travel would erase the concept of isolation for off-world colonies. A scientist on a research base on Europa could be home for dinner with her family on Earth every night, critical supplies, specialized machinery, or emergency medical teams could be sent to any corner of the solar system in moments, not months. It would create a truly unified solar system-wide civilization, where the vast distances that currently separate us become meaningless. The economic and cultural exchange between worlds would be as fluid as between cities on Earth today, fostering a shared identity and accelerating progress at an unimaginable rate. Yet, this godlike power comes with profound philosophical and ethical dilemmas that we must confront long before the technology is ever realized. The most famous is the copy problem. If the original is disassembled in the process of scanning, is the person who steps out on Mars truly the same person who stepped in on Earth, or are they a perfect copy, a duplicate with all the same memories and consciousness, while the original is, for all intents and purposes, dead? This gets to the very heart of what constitutes identity and the continuity of self. Furthermore, the potential for abuse is staggering. What prevents someone from creating an unauthorized copy? Could you teleport a bomb directly into the heart of a capital city? The development of teleportation would demand a complete rethinking of security, law, and the very definition of individual rights on a scale we have never before contemplated. It is a technology that promises to unite humanity like never before, but only if we can navigate the incredible ethical chasm it opens. But for all our theories about the universe's end and the nature of its contents, the most profound mystery of all is how it began. Every culture has its creation myth, a story to explain how something came from nothing. Modern cosmology has its own, the Big Bang. We've traced the cosmic timeline back to a fraction of a second after that initial cataclysm. But the moment of Genesis itself, the true time zero, remains shrouded in impenetrable energy. The 29th event that could change everything is the moment we finally pull back that final curtain, using observations of the very first moments of existence to reveal not just how the universe began, but why and what, if anything, came before. This quest is focused on capturing the faintest whisper from the dawn of time, the primordial gravitational wave background. In the first sliver of a second after the Big Bang, the universe is thought to have undergone a period of exponentially rapid expansion called inflation. This violent stretching of spacetime itself would have sent powerful ripples, gravitational waves, crashing through the fabric of the cosmos. Unlike light, which scatters off matter, these gravitational ripples would have traveled unimpeded for nearly 14 billion years, carrying with them a pristine, unaltered snapshot of the universe's violent birth. Detecting this signal would be like finding a recording of the first cry of the cosmos, a direct messenger from the moment of creation itself. The hunt for this holy grail of cosmology is already underway with ambitious projects like the Laser Interferometer Space Antenna, or LISA. This planned space-based observatory will consist of 3 spacecraft flying in a precise triangular formation millions of kilometers apart, using lasers to measure the infinitesimal stretching and squeezing of spacetime caused by passing gravitational waves. By looking for a specific low-frequency hum buried within the data, scientists hope to identify the unique fingerprint of inflation. Successfully isolating this signal would provide the first direct observational evidence for the inflationary model, confirming our most robust theory for the universe's initial expansion and giving us an unprecedented look at energies and scales that can never be recreated in any particle accelerator on Earth. The implications of such a discovery would extend far beyond confirming a theory. The precise pattern of those primordial waves would act as a cosmic DNA test, revealing the specific physical conditions present at the beginning. Different models of inflation and competing theories of quantum gravity each predict a slightly different pattern in this gravitational wave background. By reading this pattern, we could effectively rule out entire classes of theories and potentially identify the correct one, bringing us closer than ever to a true theory of everything that unites gravity with quantum mechanics. This would be the ultimate victory for fundamental physics, providing a single, elegant framework to explain all forces and phenomena in the universe, from the behavior of the smallest subatomic particle to the fate of the largest galaxy cluster. But the most mind-bending possibility is that these observations could offer our first glimpse of what, if anything, preceded the Big Bang. Some theories, like the conformal cyclic cosmology proposed by Roger Penrose, suggest our Big Bang was not a true beginning, but merely a transitional phase, a reset following the infinite expansion and death of a previous universe. Others, like the brain cosmology model, suggest our universe is a three-dimensional membrane floating in a higher dimensional bulk, and that the Big Bang was the result of a cataclysmic collision with a neighboring universe. The data encoded in the primordial gravitational waves could contain subtle clues, anomalies, or imprints that point to one of these fantastical scenarios over the others. We might find evidence that our universe is one of many in an endless cycle of birth and death, or that we are just one bubble in a vast, frothing multiverse. Answering the question of what came before would represent the final and most profound step in humanity's journey of cosmic discovery. It would complete the narrative that began when the first humans looked up at the night sky and wondered where it all came from. Knowing our ultimate origin story would provide a context for existence itself, a framework upon which to hang every other scientific, philosophical, and theological question we have ever asked. It would tell us whether our universe is a unique, one-off event, a rare bubble of stability in a chaotic void, or merely one page in an infinite book of cosmic history. This knowledge wouldn't give us new technology to wield or new worlds to conquer, but it would give us something perhaps even more valuable, the ultimate answer, granting us a complete and total understanding of our place within the grand, awe-inspiring tapestry of all that is, all that was, and all that ever will be. And this brings us to the culmination of our journey, the 30th and final event that stands as the ultimate testament to human maturity, our official graduation to a Kardashev Type 1 civilization. This is not merely a technological milestone, it is a philosophical and societal transformation of the highest order. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures a civilization's level of technological advancement based on the amount of energy it is able to harness and utilize. A Type 1 civilization has achieved mastery over all of the energy available on its home planet. For humanity, this means seamlessly capturing and directing every watt of energy that reaches Earth from the Sun, along with the tremendous geothermal and tidal forces generated by our planet itself. We are talking about a global society operating at a power level of something like 10 to the 16th watts, a number so vast it represents a complete and total break from every economic and political system that has come before. The most visible sign of this new status would be our command over the planetary environment itself. Imagine a world where natural disasters are not inevitable tragedies to be endured, but manageable events to be mitigated. A global network of satellites and ground-based installations could gently deflect the energy of major hurricanes, starving them of their power before they ever make landfall. Tectonic stress could be monitored with such precision and released so gradually that catastrophic earthquakes become a relic of the past, managed through a form of planetary acupuncture. Through massive, coordinated geoengineering projects, perhaps using fleets of automated vessels to brighten ocean clouds or aerosols to precisely manage atmospheric composition, we would no longer be passive victims of climate change. We would become active stewards of Earth's climate, maintaining it in a balanced, life-optimal state for the benefit of the entire biosphere. The planet would function less like a wild system and more like a garden, a work of art that we are consciously and responsibly tending. This level of energy abundance would completely eradicate scarcity as a concept driving human conflict. With virtually free and limitless energy powering our civilization, the cost of everything from clean water and food to manufacturing and transportation would plummet towards zero. Desalination plants could provide endless fresh water to every arid region on the globe. Vertical farms and cultured meat facilities powered by this abundant energy could provide nutritious food for everyone without the environmental destruction of traditional agriculture. The very foundations of our economy, which have been built for centuries on the allocation of scarce resources, would have to be reinvented around a new paradigm of post-scarcity and human fulfillment. The driving question of society would shift from how do we distribute what's limited to what do we choose to create with all that we have. Achieving this state requires something far more difficult than technological innovation. It demands an unprecedented level of global cooperation. To manage Earth as a single, integrated system, we would need to dissolve the antiquated political and national barriers that have divided us for millennia. This doesn't mean a bland, homogenized world government, but rather a functional planetary governance system focused on managing the global commons, the atmosphere, the oceans, the climate, while allowing for immense cultural and regional diversity to flourish. All of humanity would need to see itself as a single crew on a shared spaceship, recognizing that a failure in one system ultimately affects everyone. This collective identity, forged not by conquest but by shared reason and necessity, would be the true marker of our maturity. The achievement of a Kardashev Type 1 civilization is not about raw power, it is about wisdom. It is the moment we prove that we are capable of wielding the incredible forces of our planet, not for domination or short-term gain, but for the enduring benefit of all life and the preservation of our precious singular home. It is the final step in our childhood as a species and the first glorious step into our long-term future. What we have explored together is far more than a simple list of discoveries. These 30 possibilities are a map of human potential, a timeline of cosmic turning points that represent nothing less than the maturation of our species. Each event, from the smallest microbe on Mars to the mastery of the universe's fundamental forces, is a threshold. Crossing any one of them would irrevocably change our story, elevating us from a species that simply lives on a planet to one that actively shapes its destiny across the solar system and beyond. This isn't about predicting the future, it's about recognizing the incredible array of futures that are now, for the first time, physically possible. We are living in the opening chapters of this new era. Right now, the foundational work is being done. Robots are scouring Martian deserts, telescopes are analyzing the atmospheres of distant worlds, and engineers are sketching the first designs for orbital farms and interstellar probes. The dawn of the space age is not something that happened 60 years ago with the launch of Sputnik. That was the first spark. The true dawn is now, in this moment, as we stand with one foot still firmly on Earth and the other tentatively reaching out into the cosmic ocean, preparing to take our first real steps into a wider universe. We are the generation that gets to witness this transition, to see humanity's childhood on Earth begin to give way to its adulthood among the stars. This makes you, the viewer, more than just a spectator. You are a contemporary of this great awakening. The most exciting question you can ask yourself today is not if these things will happen, but which of them you will live to see. Will your lifetime overlap with the confirmation that we are not alone? Will you watch the first humans set sail for Mars, knowing they are going there to stay? Will you see the news report announcing the discovery of a true second Earth around another star? The pace of change is accelerating so rapidly that many of these transformative events are not distant dreams for millennia from now. They are plausible realities for the coming decades. Your future, and the future of everyone you know, will be directly shaped by which of these cosmic milestones we achieve next. This is why curiosity is our most valuable resource. The journey ahead is not predetermined. It will be built by the collective will, ingenuity, and wonder of billions of people. It requires the dreamers who imagine the possibilities, the engineers who convert those dreams into blueprints, the politicians and citizens who support the mission, and the storytellers who share the vision. Staying engaged, staying informed, and staying passionate about our cosmic future is how we ensure that this incredible journey continues. The greatest adventure in human history is just beginning. Let's all make sure we are a part of it. Keep looking up and never stop wondering what's next.